All right, let's get into it. We are about to pull back the curtain on one of the coolest ideas in all of tech, how machines actually learn. Now, I know it can seem like some kind of magic, but I promise, by the end of this, you'll totally get the core ideas that make it all work.
You know, we hear phrases like AI and machine learning thrown around constantly. But when someone says a machine has learned something, what is really going on inside that digital black box? That's the big question we're going to crack open today.
So, first things first, to really get this, you've got to understand that AI, machine learning, and deep learning aren't just buzzwords you can swap around. They're actually nested inside each other, kind of like those Russian dolls, where each one is a more specific piece of the bigger one.
So at the very top, the biggest doll in the set is artificial intelligence, or AI. This is the big, overarching dream, right? The original goal of creating machines that can think, reason, and act in ways that we would call intelligent.
Now, pop that one open and inside you'll find machine learning. And this is where things get really, really clever. See, instead of a programmer sitting down and writing a million lines of if this then that rules, we do something different. We just show the machine a ton of examples and let it figure out the rules for itself. It's all about learning from data.
And finally, the innermost doll, the one that's causing all the excitement lately, is deep learning. This is a superpowered type of machine learning that uses these amazing structures called neural networks, which are, well, they're loosely inspired by how our own brains work. The deep part, that just means these networks have lots and lots of layers, which lets them learn incredibly complicated patterns. This is the engine behind almost every big AI breakthrough you hear about.
Okay, so to make this feel real, let's start with a really simple example. Forget about recognizing cats in photos for a minute. Let's see if we can teach a machine to do something basic. Convert temperatures from Celsius to Fahrenheit.
But here's the catch, and this is the important part. We are not going to give the computer the formula. You know, multiply by 9/5, add 32, none of that. That would just be programming. No, we want to see if it can learn the relationship all by itself just by looking at the data.
So here's what we do. We just feed the machine pairs of numbers. We tell it, hey, 0 degrees Celsius is 32 Fahrenheit, and 20 Celsius is 68 Fahrenheit, and so on. The model's only job is to try and find a mathematical line that connects all those dots. It's not thinking, it's just finding a pattern.
So after it's seen just a handful of these examples, we hit it with a test it's never seen before. What is 100 degrees Celsius in Fahrenheit? And look at that. It spits out 211.99. The real answer is 212. It's practically perfect. Just by looking at data, it learned the formula without us ever telling it. That right there is the magic of machine learning.
Okay, so a straight line is great for temperatures. But what about something truly complex, like recognizing a face in a crowd or understanding human speech? Those patterns are way too messy for a simple line. For that, we need something much more powerful. We need to build a kind of digital brain.
And that's where the neural network comes in. You can think of it like taking that simple line-fitting model we just saw and putting a whole team of them to work together, organized in layers. Each one of these little neurons is a tiny decision maker, but when you connect thousands or even millions of them, the network as a whole can learn patterns of just staggering complexity. This is the absolute core of deep learning.
So, how does this brain actually get smarter? Well, the learning process isn't just one thing. It's really a cycle that relies on 3 key ingredients, all working together perfectly.
So what are they? First, you have the activation function, which is like the little decision maker in each neuron. Second, there's the loss function. Just think of this as its report card. And third, you have the optimizer, which is basically the study plan it uses to get a better grade next time.
Let's start with the activation function. This part is absolutely critical. Without it, a neural network could only ever learn simple, straight lines, just like our temperature converter. What these functions do is introduce bends and curves into the math. They act like little dimmer switches, deciding how much of a signal gets to pass through a neuron. This allows the network to combine all its simple lines into the incredibly complex shapes needed to understand the real world.
Next up, the report card, the loss function. Now, I know the math formula on the screen might look a little intimidating, but don't worry about that. Its job is actually super simple. It just calculates one single number that tells us exactly how wrong the network's guess was. And that's really all there is to it. The entire goal of training one of these models is to make that wrongness score as tiny as possible. If the network makes a perfect guess, the loss is 0. If its guess is way off, the loss is a really big number. The whole game is just a hunt for the lowest possible score.
So the network gets its bad grade. Now what? It needs a plan to do better.
That's the optimizer's job. It looks at that wrongness score and uses some clever calculus to figure out exactly how to tweak every single connection inside the network to make a slightly better guess the next time around. This is the engine that actually drives the learning forward. But here's a fun twist. It turns out there's more than one way to optimize. Over the years, researchers have come up with different strategies, each with its own strengths. You can think of it like different ways to study for a big exam.
On one side, you've got the classic stochastic gradient descent, or SGD. It's the most basic approach. Just figure out which way is downhill toward a lower score and take a tiny step. But then we get a great upgrade: momentum. Instead of just taking one step, it starts to remember the direction it's been going. It's like a ball rolling down a hill. It builds up speed and doesn't get sidetracked by little bumps. This helps it get to the right answer way faster.
And that brings us to the modern-day champion, an optimizer called Atom. Atom is so smart. It takes that great idea from momentum, but it adds another trick. It actually adapts its learning speed for every single connection in the whole network. Some parts can learn really fast, while other, more sensitive parts learn more slowly. This amazing adaptability is what makes it so incredibly efficient, and it's why it's the go-to choice for pretty much everyone today.
So just to wrap up this little showdown, the table says it all. SGD is simple, but it's slow. Momentum is definitely improvement, a good speed boost. But Atom? Its mix of speed and adaptive intelligence makes it the fastest and most reliable way to get that wrongness score down to 0, which is why it's pretty much the industry standard. So there you have it. We've gone from the big fuzzy idea of AI all the way down to the nuts and bolts of how a machine actually improves, one tiny step at a time. It's not magic at all, is it? It's just this elegant cycle of making a guess, measuring how wrong you are, and then intelligently updating your strategy. And knowing that, it leaves us with one last, really exciting question to think about. What are we going to point this incredible learning